So last time we talked about a couple of gotchas in plane elasticity with respect to um, volumetric locking, uh, plane stress, the volumetric locking, I'm sorry, in plane strain, volumetric locking occurs when the Poisson ratio approaches a half. And then in plane stress, you have this artificial stiffness. That's this sort of just a defect of the element construction, right? And we can alleviate that with under integration, but then that introduces other instabilities and everything. So, sort of along that theme of being able to see if an element, given element formulation, will converge to the exact solution, we typically use something in finite elements called a patch test. Okay, so a patch test is a sort of numerical experiment, and there are actually multiple patch tests that we can use. Okay, the one I'm going to describe is probably the most common, and if somebody just says the patch test, this is probably what they're referring to. It's essentially, it's just like, for the most part, when somebody says the finite element method, they're talking about either uh, triangular or quadrilateral elements in 2D or tetrahedron or brick elements in 3D with linear interpolation. Of course, you can go higher order, but usually when you start talking about higher order, you start talking about HP methods, HP finite elements. Um, so, typically when somebody says the finite element method, they're talking about linear interpolated elements. And so when somebody says the patch test, they're usually talking about, does a patch of elements, will it recover a linear displacement field? Exactly, okay? And um, because a linear displacement field should reproduce a constant strain or a constant stress, a lot of times we just look at the strain or the stress to understand if it passes a patch test. So to construct a patch test, oh, what we want to do is we want to take a patch of elements and so a patch meaning more than one, right? So we'll sort of want to take the minimal number of elements that we can get by with. It's also kind of important that the elements are not regular because some formulations will pass a patch test for regularly shaped elements, but not for irregularly shaped elements. So I want to take a patch of elements. This would be 4 quadrilaterals in 2D. And we'll want to minimally constrain the system such that we remove the rigid body degrees of freedom, right? So we have to apply some constraints because, if we assemble this, the stiffness matrix would be singular. But we can apply a sort of minimum number of constraints, which in this case would be that, right? So we're going to pin the corner. That's going to prevent any translation, right? And then if we apply one roller there, that will prevent any rotation. And then we're going to apply a force. This distance here is h. And since the elements are linear interpolated and the distance h is equal, we can write down what the equivalent stress would be, or expected stress would be in terms of the force. So if we apply a force that's equivalent to 1/2 sigma x ht, okay, where sigma x is some constant stress, and if we solve this problem, we should be able to reproduce exactly that stress. So when we compute the stress up there, right, we'll have constant stress in the elements if they're linear interpolated. The stress that we compute should be exactly sigma x. And when I say exactly, I mean to machine precision. Right? It should be exact. Okay? If it does, if it will, it passes the patch test. And this implies that it will converge to the exact solution. So converge meaning as I refine the mesh, if I have an element formulation that passes the patch test, as I refine the mesh, it will converge to the exact solution. Okay? If it's stable. Right? So if the element's stable. So we're saying the element doesn't have some defect like the underintegrated elements do. Okay? So if the element's stable, and the easy way to test for stability is to look at the eigenvalues, right? Once we pin it down, once we rid ourselves of the rigid body modes, then all the eigenvalues, there should be no non-zero eigenvalues in our matrix. If there are, then there's some element defect, which usually comes from underintegration. Okay, so this is a test. It's a little numerical experiment that we often use with new discretization formulations, new elements, it's just something quick that we can do to help us understand if we have something that's going to converge. So when somebody asks you, did you do a patch test, or will it pass the patch test? Now you know what it is. So there's also something called the weak patch test. And a formulation is said to pass a weak patch test if it fails for a coarse discretization. So if we have a coarse discretization and it fails the patch test, but we refine the mesh and all of a sudden it begins to pass. So at further refinements it begins to pass the patch test. Then we'll say that, well, it patches, this element formulation passes the weak patch test, or it's weak patch test consistent. And the reason for this is it usually also has to do with integration, because if I have some irregular formulation of elements at the beginning, as I refine them, they begin to look more and more like parallelograms, right? So these, even if I have, in this case, it's not that irregular, right? But, even if this element, if we look at this element here, sort of irregular shape. If I just do multiple refinements on it, eventually down here I get something that looks more like a parallelogram versus an arbitrary quadrilateral. And again, that would have something to do with the numerical integration scheme. That there's some inaccuracy for an irregular element, but because remember, the Gauss integration is exact for the fine translations and dilations. So if I have a parent element and I just, parent element's always a square, right? If I just make it bigger or make it smaller, or rotate it, I'm still going to have exact integration via Gauss scheme. It's only when I sort of create some non-affine deformation and I have some really irregular shaped element that I have an inaccuracy in the Gauss. Yeah.
So do you have to perform the patch test like this during your simulation like you have large deformation and the elements are like
No, what you would do is you'd do it first, right? So you came up, I mean, most of the elements that are, say, in abacus or ANSYS, we know them to be, they pass a patch test or weekly or whatever, right? We don't necessarily need to go through the exercise. But it always might be useful just to understand if you're using the code properly, applying the boundary conditions properly, something like that. But so this is something you do up first. You know, once you have a new element formulation or something, you implement it. You'd solve some minimally constrained group of small elements like that and see if it passes a patch test. If it does and it's stable, then when you go to your million degree of freedom system, you can trust that you're converging to the right answer. Because here it will, we can prove that it'll converge. I mean, and also this is a, this is a numerical test, but there are mathematics behind it that you can prove that if this works, then you can, it will converge to the exact answer in the limit, right? So, but in a real, arbitrarily shaped domain, we don't know what the exact answer is, okay? But because we've performed the patch test and we know that it passes the patch test and it's stable, we're trusting, right, that it's going to converge to the right answer. And just as an aside, as sort of an analyst, a lot of times in academia and in mathematics, we always do these convergence rate plots where you compare your numerical approximation to the exact one. And that's sort of the goal of the whole paper you write, or the goal of everything you're doing, just to create these convergence rate plots. But if you find yourself as an analyst, you got to solve problems, right? You don't have an exact answer, right? So you don't really know what it is you're converging to. I mean, you hope you do everything right beforehand, and you can trust what you're doing. But then you need to do. I mean, you can't just go and solve a problem and say, oh, it's correct. Right? There's no way to know that the mesh you chose is the right mesh, and it's refined enough to resolve all the discontinuities and all that, right? So really what you have to do is you need to do a convergence study. You need to take a series of consecutively refined meshes and look for the maximum, look for the quantity of interest that you're interested in, right? And whatever quantity of interest you're interested in. If you're a mechanical designer, it's probably stress, or if you have plasticity, plastic strain or something, right, that you want to look at, and there's only so much you're going to tolerate. And so any areas of high stress concentration or anything like that, you want to sort of focus on that and then do a series of mesh refinements. And what you want to look for is that your solution doesn't change. Again, this is just a rule of thumb as an analyst. What you would look for when you can claim you have a converged solution is when your solution doesn't change from one refinement to the next more than 5% or something like that. Right? At some point, we'd all love to have perfectly exact answers, but there is a practicality and reality. But you do have to do a series of refinements so that it is converging to some answer. And once you've gotten to the point where one refinement doesn't change beyond the other one more than, say, 5%, that's just a rule of thumb, right? Then you can say, okay, I've got a converged solution. And, you can take those results as the truth. Right?